information element fuzzer. Let's see at the example to the left. So there is a buffer which contain there is a buffer that can contain up to 512 bytes, but McAfee specification specifies that frame body can be up to 2312 bytes long, and this buffer is used to contain all the almost all the frame body except the fixed parameters. So the driver, while parsing association response frame, copies the total contents of all the information elements within the frame into this buffer, except the headers. It gives the attacker a way to so it triggers the vulnerability, whether it's a stack or a heap or pool vulnerability. So summary. It's not enough to fuzz only information elements. Total frame size also matters. And this example demonstrates also that the space for placing the kernel mode shellcode in the frame is drastically increased. So you can place the payload larger than the 255 bytes in the frame, and this payload may get executed. Well, yes, there is an underflow actually in this example as well, but forget about this underflow for the moment. The second example: can the attacker place shellcode inside more than one information element? This example shows that it's possible to do. Vulnerability cannot be exploited in this example by a single information element. So, for example, it's not possible to exploit this code by sending malformed supported traits elements only, or rates element only, or extended support traits element only. But there is a stack buffer size is 16 bytes. It's the extended supported traits. And the code copies up to 16 bytes into this buffer. So it's okay. But what about the rates count internal variable of the AP-info internal structure that you can see to the right in the right top corner? Let supported traits be 17 bytes long, and extended supported traits contain up to 255 bytes. So both are copied in this example into the same buffer on the stack. 16 bytes are copied to the buffer while processing the supported traits element, but the rates count variable is set to 17. So when parsing the extended supported traits, this code will call the ndSmooth memory, and ndSmooth memory will copy minimum out of 16 and 16 minus rates count, which is -1. So guess what will happen with the driver. This example is given on this screenshot. You can see that the association, you can see the beacon frame, but containing supported traits element 17 bytes long, and the followed by extended supported traits element 255 bytes long, containing all A's. So important points from these two examples. In fact, let me go back to the example 2. There is a case tagged. The driver also processes SSID information elements and there is also a vulnerability there. But this vulnerability and the example I'm describing in the white paper, it demonstrates that even the contents of the information element may trigger the vulnerability, not only the length of the information element, but a specific byte set at a specific position in a specific information element. So please refer to the white paper for that one more example. Important points. Multiple information elements are entangled. Vulnerability is triggered if both supported traits and excuse me, it's an error. If both supported traits and extended supported traits are present, an attacker can place the payload within more than one information element. Maximum payload length is not limited by 255 bytes. So to be able to do penetration testing of wireless LAN drivers, the penetration tester needs to have a setup of the following systems. The injector system, having any wireless driver patched for injection. The backtrack final is, or the older auditor Linux Live City is very useful for penetration testing of wireless LAN drivers. And the system should have some kind of fuzzer. The tester can use Larcon, Ruby Larcon extensions in Metasploit 3.0, or the homebrew fuzzer that we described early. For raw injection, using the fuzzer from the previous slides, it is necessary to configure a wireless interface for raw injection. Meta Wi-Fi NG doesn't support anymore raw def syscontrol. So to configure the wireless interface for raw injection, you will need to execute the following config script. The sniffer system. Typically, Wireshark can be used for most of the purposes. And don't forget to listen on the same frequency, on the same channel, because sometimes it's really annoying when after a couple of minutes you understand that you're listening on a different channel than injecting. If you are testing in the environment that has lots of access points, then it is fairly easy to sync in the amount of beacons or probe responses or other frames sent by all those access points. So the Wireshark gives you a good way to filter the sniffed frames. So for example, you can filter only beacons targeting specific destination address, or filter only association request and response management frames. And finally, you will need a system under investigation which runs which has a target wireless adapter running target driver and some kind of kernel debugger, like Softice or Windows debugger. Two first systems can be combined into a single system if you have two wireless cards, for example, PCMCA and USB card. This is a just brief introduction into the environment, and the other reference is given by David Maynard in the Beginner's Guide to Wireless Auditing. All right, so for the complete picture of remote exploitation of wireless LAN drivers, we will need to give a simple example of harmless kernel mode payload on Windows. Specifically on Windows, that can be used for demo purposes. So the harmless kernel mode payload. First, we need to find a trampoline address to redirect an execution to our shell code. The trampolines are the same as for user LAN shell codes, and in case of, for example, stack-based overflows, they are call ESP, jump ESP, push ESP read, or some other instructions. So it is fairly easy to search for these trampoline addresses in debugger, for example, in Softice, or in the using the s command, or in the Windows debugger. Using the same as command, actually, or any other tools like find jump 2 or find opcodes tools, fully available. For simplicity, I will use the hard-coded and TOS kernel addresses to resolve addresses dynamically. It's not, in the shellcode. It is necessary to one may use the vectors in the IDT table to get some address inside the NTOS kernel image and search lower memory addresses for MZ signature to resolve image base of NTOS kernel, and then parse its export tables. Then the shellcode will have the function addresses, necessary native function addresses, but it's not the purpose of this presentation. So as Bokchak and Scape wrote in the paper, the kernel mode payload can be broken down into several stages: migration stage, stagio stage, the actual code being executed, like useful payload, and the recovery stage. So we don't use the stagio stage because we don't need to port, for example, userland shellcode and execute it. It's the simple case of the payload. So the migration stage. First of all, the migration stage implies that the shellcode needs to drop IRQL to passive level, because it will allow the exploited thread to be preempted by Windows thread scheduler, and this will avoid freezing the system upon recovery. Basically, there are lots of other disadvantages of running shellcode in dispatch level, so it is basically impossible to do so. So shellcode cannot, dispatch level cannot take the page faults. It cannot call most of the functions, for example, like synchronization functions like sleep and wait for single object and so on. So the first that shellcode, kernel mode shellcode does, it drops its IRQL level to passive level. Then this payload, for demo purposes, does something useful on the display stage. It resets the screen and displays the string owned on it using native boot video driver functions. Acquire display ownership, reset display, display string, and so on. It's fairly visible result of that the payload got executed during the exploitation of the wireless driver or any other driver. The recovery stage, it's a very important stage because the kernel mode payload doesn't want to. The attacker doesn't want to lose all the results after returning from the shellcode execution. There are a number of ways of smooth return from the kernel mode payload. One of the well-working results is given here. It's the payload can yield execution in a loop to other threads, so it will not freeze the system, and it doesn't impact performance too much, but the drawback is that the wireless will not work correctly because one of the wireless driver threads, exploited threads, will loop and will do nothing except printing owned string into the debugger and yielding execution. So most of the references, most of the information about the designing kernel mode payload on Windows can be taken from the Barnaby Jacks Step into the Ring Zero paper and Bokchak and Scape's paper. Oops. So did anyone already launch the payload I described? So okay, this is actually the result of that payload that I've just described in